All right, we're happy to have Bibek Bhandari as our next speaker. Go ahead, Bibek.
So yeah, thank you. This has been the work we have been doing for like last year. It's based on quantum feedback thermal machines, and so we have been doing varieties of work. So I won't be going into the details of each one of them, but instead I would like to give an overview of the works we have been doing here. And if you have any questions in the middle, just feel free to interrupt me, and I will go into the details if you want. We have been doing this work under the supervision of Professor Andrew Jordan and Khan he's a grad student now in University of Rochester. He did his master's thesis with Andrew. So he worked on one of the topics. Robert is a graduate student in Rochester. And my all-time collaborator, Paolo, is involved as well. So we are these 4 people collaborating on this work. So the outline of my talk would be the first part. I will talk about single qubit-based Maxwell's demon. I think it has been reiterated many times in this seminar, but I will take a different approach and align it with the error of time concept, how you can link different thermodynamic aspects of a single qubit-based Maxwell's demon to error of time. Then I will talk about coupled qubit-based Maxwell's demon. The reason why we go to coupled qubit is that in that case, you can look for collective effects. You can think of 2 setups in parallel, or like you can do simultaneous measurement of the qubit. And you look if the parallel setup is better than the collective one, or the collective one is better than the parallel setups. So that's our main reasoning behind studying the coupled qubit system. Then we will go to the measurement assisted refrigerators, where we will have, like, instead of where a Maxwell demon, we have like 1 thermal bath. In this case, we'll have 2 thermal bath, 1 hot and 1 cold, and we'll use measurement and feedback, and sometimes only measurement to push heat from the cold bath to the hot bath. And finally, this is an ongoing research work. We have some preliminary results. I will show you those. It's a work we are doing on studying optimal feedback in these measurement-based thermal machines using reinforcement learning. So these are the literature, some of them. So the first 2 my talk would be mostly concentrated on the first 2 work. I will talk something from the last work here, which was recently published, and there will be some talk about the 3rd article here, which is ongoing. So just to give you an overview of how the particle energy transport happens at nanoscale, I always keep this slide just to motivate the audience. Let's say, so usually we have a quantum system attached to a hot bath and a cold bath, and heat and transport are motivated by, let's say, the difference of temperature or the difference of potential between the 2 leads. So you can have different kind of scenarios here and play with it. And there are like tons of literatures where people have studied this system, this setup with different systems and different reservoirs, different couplings, different types of driving, let's say, and different kinds of biases and studied charge and transport. But what we have more to that is a measurement. So what we want to do is that we also want to include the measurement on top of this. So let's think of a simple setup where we have a system, which is a 2-level system, let's say. And we have a thermal bath, which is given by L. And on top, we have a measurement probe, which does some kind of measurement. And when we say measurement, we usually talk about incompatible measurements, right? So because we want to have some effect of the measurement on the quantum state of the system. So let's say the system is in 1-1 basis, and the measurement observable is in like 0-1-1-0 sigma x basis. Then I can calculate the heat current flowing out of the bath L, right? It's a very simple master equation calculation when you say both the coupling as well as the measurement is weak. You can see that this heat current is always negative, meaning there is no way you can extract heat from the hot bath or the bath L there. So it's all, the measurement is always dissipative in nature. So, and then you can, this is for, I think I did this thing for like fermionic system. You can do it for also like bosonic system, you get the same answer. And you can also do one other thing. You can think that measurement probe to be an infinite temperature reservoir. You can replace the measurement probe with an infinite temperature reservoir, you will end up with the same expression over there. So until and unless you take the measurement to be in the sigma x basis when the system is in sigma g basis. So that's the kind of like mathematical equivalence between infinite temperature reservoir and the measurement probe. So the conclusion from this slide is that measurement inevitably leads to dissipation in this kind of incompatible measurements I showed here, and feedback should be applied to obtain cooling. So that's why we want to include feedback on top of this measurement. What are the different steps involved in, let's say, the first kind of thermal machine where we have a Maxwell's demon using single qubit? So in step one, we just thermalize the qubit with the reservoir. So we start from a thermal state. And in that case, let's say we are in the negative z-axis, and we do a measurement along the x direction, and then we get the qubit or the Bloch sphere in the xz plane. We apply feedback, bring it back to the z direction, and then thermalize back again. Without stressing a lot, because I think this has been discussed many times during this workshop. So this is the same basic principle where you do incompatible measurement and you rotate back and you thermalize your qubit, extracting the amount of work that is given by the difference in length of the Bloch vector. So let's go like slowly. Step one, we have the thermal state. It's a very simple system. So I can write the thermal state very easily. I have the initial energy E0. N bar is the Bose distribution. I think it's pretty much textbook everything here. Then we do measurement. So Demon performs a measurement, let's say, with these cross operators. And you can clearly see that there are different regimes. So when kappa goes to 0 or 1, then you have the maximum measurement, and when kappa goes to 0.5, there's like the weakest possible measurement. You don't extract any information. So you can replace kappa with 0.5, and you see that both of this thing max terms cancels out, and you just have this term with the identity. So the measurement doesn't do anything. You don't extract any information when kappa equals to 0.5, but you extract maximum information when kappa equals to 0 or 1. And you can relate this kappa to gamma and delta t, where gamma is the measurement strength and delta t is the measurement time. So simply, you can write the state of the qubit after measurement as rho m plus minus. It's a very simple expression, which we say as forward measurement probability, because we do the measurement in time delta t. Similarly, we can define a backward measurement probability by doing a time reverse measurement and trying to see if we get back to the same place or not. Because it's an irreversible measurement, so we don't get back to the same place. There's a difference between forward and backward probability, and the difference is written in terms of error of time. So which way you are going, forward or backward, right? So the error of time would be the logarithm of this forward probability divided by the backward probability. And the backward probability is given here, which is like just the probability based on you made a forward measurement. What is the probability of making the time reverse measurement on that? So, so we have the entire thing about, I mean, the main gist of this first part of the this talk would be to link different thermodynamic quantities to this Q, the error of time, which is just the logarithm of like forward and backward probability. So we already see that the energy of the qubit after measurement can be directly related to Q there, and the initial conditions given by omega 0 and G0. So this is just again highlighting what we do. We start with the thermal state, we do the measurement along the x direction, we get back to the xz direction, right? And then we do the feedback, is just rotating it back to the negative z direction. The length of the Bloch vector changes, we extract the amount as work. So what is the extracted work? Let's say, what is the energy after the end of the feedback and the measurement? So this is given by this expression, and you can clearly see that it depends on Q. That's the, so the summary of this expression is that the work extraction during all this process depends on one single quantity, Q, and the initial conditions, nothing more than that. But the most interesting thing, I think, is that because this Q gives you the irreversibility in your measurement, right? Because it somehow gives you the difference between the time reverse component. So it should be linked directly to the entropy. And you can clearly see that the entropy production due to measurement is given in terms of Q and the initial condition.
So yeah. How do you start the backward trajectory from which state?
So you do a forward measurement, right? And you have a particular probability for having that forward measurement. And then you do a time reverse measurement on that thing. So the same, yeah. The time reverse, so you have like, let's say the cross operators M, and you have the time reverse component of the cross operator M, right? So let's say M minus delta T, sorry, not minus delta T, M prime, let's say. So you do M prime over that M. And in this kind of system, we also try to study, like, let's say it works as a refrigerator, which takes heat from the reservoir, cooling the reservoir at the end. So if you have a shorter block vector, then you extract heat to make it longer back again, right? And this beta would be given the amount of energy extract, which is given by the difference of energy. Let's say E0 is the initial energy and EF is the energy of the qubit after feedback. So the difference of the energy on top and divided by the cost of doing that, performing that process. So they're like energy of the qubit after measurement, there is the energy cost of information. So you have to erase the information that gives you WER, and the energy of the qubit after measurement subtracted with the initial energy gives you the amount of work you perform on your system. So, and what we do is that we plot the coefficient of performance as a function of measurement strength kappa. And if you remember, kappa equals to 0.5 means no measurement at all. Kappa equals to 0 and 1 means a strong measurement. And we see that the coefficient of performance shows a maximum as a function of measurement strength. So it's not like you do like projective measurement and you get the best possible heat extraction. That's not the case. There is our best performing machine. There is like a sweet spot where you get the better refrigerator when you compare with measurement strength. And I think this is the most interesting plot here because it relates directly the entropy production with the error of time. And if you look at the total entropy production, right, minus delta SM, or like the entropy production due to measurement, you see that the Q, as a function of Q, the delta S increases. And the delta SM, the delta S total goes down because at the end of the process, you are extracting heat from the reservoir. And this is given in terms of so if you sum over also the entropy production for eraser, then you get like the sum of the two would be given by the black dashed lines over there.
Just, do you have an intuition for why, I mean, the projective measurement is not the best for having the best coefficient of performance?
Not sure, but I think the reason is that it's not a very simple relation, right? It's the ratio between the two, like the work and the heat extraction, I mean, that plays a role. So it's not that always you get the maximum for each of them for one measurement strength. That's the reason, I guess. Now we also do the same thing. The previous case was with discrete measurement. Now we expand this thing to continuous measurement case. So we have like forward and backward measurement given by the forward and the time reverse component of the forward. You do the sigma x to minus sigma x, or vice versa. And here delta T is the time allocated for one measurement. So if you make delta T very small compared to the characteristic time tau, you get a very weak measurement, right? So that's how we play with the weak measurement. And tau is the characteristic measurement time because you need to compare delta T with something. That gives you when the let's say the two measurement outcomes can be well separated. And in this case by two standard deviations. And R is the measurement record we obtain, different in experiments, but in simulation, we take them from two Gaussian distributions centered around plus and minus 1 because we are doing sigma x measurement. So the nicest thing about this continuous measurement was that we were able to find a nice expression for the probability distribution of work extraction. So if you see on the top hand side, so we have a probability distribution of our work extraction in terms of work extraction. So if you keep putting these terms back into the equations, then you will find PW extraction can be written in terms of W extraction. And we plot this thing as a function with the numerical simulations, and you see there is a perfect alignment with the analytic results, which is kind of nice. So this is kind of something that I think is experimentally accessible as well. So it's something like this was the highlight of the paper, let's say. And we could also do the similar thing with heat distribution. What is the heat of the measurement and stuff? And we had a similar outcome with simulation. So, yeah.
Have you, I'm just curious mathematically, have you tried to see like is set expression for probability of work extraction in terms of WEXT?
So, I mean, you can do that, but I don't think it's a very complicated expression even now, right? So we tried, but it looked like a very complicated expression, so we didn't go further. But I mean, if you just write it this way, I think it's kind of clear that you can write PW external in terms of external. So that was the story about the single qubit. Now we wanted to move on to couple qubits, and this is we published this paper recently, and it was highlighted as cover in the Entropy Journal, the February volume of it. So it was a nice thing, a good advertisement, I think. In this case, we have, instead of one qubit, you have two qubits, and we have like the coupling is given by delta X, delta Y, and delta Z, where they are like sigma X, sigma Y, and sigma Z type coupling between the two qubits. But for the case of Maxwell's demon, I will just consider delta X, delta Y to be 0 because it's much easier. In that case, the Hamilton is diagonal, and then we don't have to worry about diagonalizing it and all this stuff. But it can be easily extended to those cases as well. Then the same thing, again, we do the initial density matrix, we normalize the two qubits, and then we do measurement in one qubit or both qubits. So the main goal of this project was to see if the parallel calculation was better than the simultaneous or not. So if we can get some collective results which can be better than the individual measurement of each qubit. So the discrete quantum, so we also do both of them here, the discrete as well as continuous. So in the discrete case, we have like, let's say M1 plus minus for 1 and 2 would be first and the second qubit. We have the same expression for both discrete and continuous measurement. Now, instead of one qubit, we have like 2 qubit to measure. And we have individual measurement where we take two parallel setup, one setup here, one setup here. We do one measurement in qubit 1 here, measurement in qubit 2 here, and we sum them up. And in the combined measurement, what we do is that we do simultaneous measurement of both qubits at the same time. And we look into the heat extractions and everything we looked for the single qubit case. So, so these are the expressions we obtained. So you see here, it's like the individual measurement has just one unitary rotation. The combined case has 2 unitary rotations for like both qubits. And then, and the energy of the qubits after feedback would be given by similar expression depending on the state after feedback. And the heat extraction would be given as a difference of the initial energy minus the final energy. So, so this is like single qubit discrete measurement feedback. We have 2 qubits, but we only do measurement in 1 qubit. We leave the other qubit unchanged. The good thing about this calculation is that you see the heat extraction depends on the coupling strength. So by increasing the coupling strength, you can increase the heat extraction from the qubit, the single qubit. So although you're not doing anything to the other qubit, you're somehow extracting heat just by the fact that you're coupling it to the other qubit. So having 2 qubits instead of 1 is fruitful even if you're doing single qubit measurement. And these are the results in terms of kappa 1, which is the coupling strength. You see that if you, depending on whether you do positive G rotation or a negative G rotation, you get cooling for different coupling strengths. So they get flipped. So you see that delta G equals to 0 and delta G equals to 0.05 give you heating when F1 equals to +1, but they give you cooling when F1 equals to -1. +1 and -1 means whether you go to the positive G direction after feedback or you go to the negative G direction after feedback. So it really depends on how you should do the feedback depending on your coupling strength. So depending on your parameter space and your measurement, you change your feedback to get the heat extraction. And here in this case, we saw both qubit measurement, like we measure both of the qubits and we do feedback on both of the qubits. And we saw different possible feedback, +1 in one, -1 in the other one. So we rotate differently the 2 qubits. And so you see that, so in some regions you get cooling, in some regions you don't get cooling. So in order to extract it, you need to do the right feedback in both of the qubits. Now, the main result of this paper, I would say, is that to see what is the individual case plus the combined case. So individual would be two parallel setups, just summed over them. Combined would be simultaneous measurement of the two qubits. And you see, as a function of delta G, there's a clear regime where you get better cooling or better heat extraction with combined measurement or sequential measurement. So this region here is the collective effect compared to what you will obtain with doing just two single measurements, right? So,
in the previous slide, it seems like the combined case well works actually in this case.
In this case,
because,
yeah. Yeah, that's true. But I think we took different parameters. I'm not totally sure if they are the same parameters, this one and that one. I have to check. But combined would be, I think it should be at least double or similar to the single measurement. So could be different parameters.
And how does it compare to the case in which you have one single spin per qubit?
Oh, so you just need to take delta G equals to 0, right? In this case, if you take delta G equals to 0, that's the single qubit case. And that exactly, because if you have delta G equals to 0, the other qubit is totally uncoupled, you don't get anything.
Okay.
So, okay, so this is, and then we also did the continuous measurement and feedback, and you see we studied heat extraction with on the single qubit measurement, and this one is combined measurement, and this is like the single qubit measurement, and for different values of delta G, and you see for some values of delta G, we get better cooling even with continuous measurement. So the continuous measurement as well says that if you have coupling to other qubit, you get better heat extraction on average. And this is the plot for like individual and combined case in like combined measurement. And you see that the red dots and black crosses give you the individuals and the combined case, and the line, they give you the standard deviation or the fluctuation in the outcome. And so we see that almost for every value of delta G, the combined case is better on average than the individual, like the parallel measurement and feedback. So somehow this both discrete and continuous measurement validate this argument that the collective effect is gives you better cooling effect in 2 qubit setup. Now, for the third part, as I told you before, we will leave the one thermal bath scenario and we will go to 2 thermal bath scenario. We will have a hot bath and a cold bath, and we have like a couple qubit in the middle. And for this, because we have like very weakly coupled baths and weak measurement, so what we do is that we use the master equation, which is additive in this case. So we have a component with like the unitary component over there, HS comma rho t. Then we have the effect of the bath, which dissipation due to the baths, and there is a component in the Lindbladian which has the measurement probe contribution. And the measurement probe contribution is like one term, which is like the average outcome, and the other one which gives you the noise. In our case, we take the noise as to be a Gaussian noise with variance delta t. The delta t would be the time you allow your measurement. I have given the form of dx and hx here. So, and then, so we do measurement, but we also do some kind of work on the qubits. We swap the 2 qubits after measuring without looking into the states. So whatever the states they are in, we just swap them, the 2 qubits, and we look into the heat extraction from the cold bath. And the reason we do this is that there was this paper by Campisi and Rosario Faggio where they had like 2 qubits, uncoupled qubits, and they looked into each qubits, and then when they find one qubit which they want to cold or like a cool is in the ground state, they just attach the bath to it. So they're like just looking into the best possible configuration of the 2 qubits so that they can cool one of their thermal baths. But instead, what we have here is a coupled qubit system, right? So we were not sure what happens if you couple the 2 qubits and you do the measurement. And so in this case, we also have weak measurement on top of the strong measurement they had. So we find that if you just do the swap operation, then average without feedback, you almost get no cooling, but average with feedback, you can get like some cooling effect. And the red and the blue line, they are like with the noise term. Without the noise term, the average is with the black dashed line. So it looks like if you do swap after measurement, you get a better cooling effect compared to if you don't do swap. But the point is that you don't need to do the swap to get the cooling effect. You can just do, you can just get the cooling effect just by measurement. You can, it's just like if you do continuous measurement on the local basis and you study the global, you have a global system and you do the measurement on the local basis, you can somehow extract the heat from the cold bath and dump it to the hot bath as well as the measurement. And if you look at this figure here, then you see that for the range of values, you see that for gamma m equals to 0.04, at the maximum value, it looks like without measurement is better. But in some other regime, it looks like for entire values of theta, which is like how you, if you swap or you change by just by a few angle, it looks like measurement and feedback always gives you better cooling compared to just measurement induced cooling. So measurement and swap, sorry, or measurement and some unitary rotation. So the main message from this part is that there is, so if you have like a couple qubit system and two reservoirs, you can take or extract heat from the cold reservoir without doing feedback, without doing any unitary rotation, just from the local measurement of the global basis, right? But if you do also some kind of rotation, then you can extract even more heat from the cold bath. Let's go to the part 4. In this case, we are thinking about using reinforcement learning for some more complicated system where we can't have analytic results very straightforwardly. So we are trying to find, like, let's say, optimal results for like, let's say, power efficiency trade-off and stuff like that. So without going into the details, the reinforcement learning is based on the principle that we have a system, and this is attached to hot and the cold bath, and there's a detector which gives you the outcome of the system. So it says, okay, what is your system state at each point? And this system state is fed back to the computer or the neural network. And then this neural network somehow optimizes your dynamics, or optimize, it eats all your information, and it gives back, it gives you back the action you have to perform to the system to get optimal output or optimal stuff that you want. So at the end of the day, what you have is that you give, the system gives the state to the computer, and computer gives the action to perform to the system. So what do you want to do? Do you want the gap bigger, smaller? Do you want to attach the thermal bath or not? Do you want to have two thermal baths, one thermal bath? Do you want to couple the two qubits or not, depending on your problem? So that's what the computer gives you. And so this is just a detail. I will skip it. This is the preliminary results we had recently, and then we are still working on it. We have some more results, but I will just highlight this result. And okay, so let's consider a qubit coupled to an environment. We can do measurement, as I showed you, in an incompatible basis, and we can do a feedback with the unitary rotation, right? So in this case, what we gave to the computer was like, okay, we do different feedback, different measurement, and depending on different states of the system, we give it to the computer and ask the computer, what is the best possible protocol? Like, should I attach to the thermal bath? Should I do the measurement, or should I do the feedback? By what angle should I rotate? And after some run, so this is the run time. So after 350,000 steps, the computer tells me what you have to do is that you have to thermalize, and then you have to do like rotation back to the z-axis, and then thermalize again. So it just says that you thermalize, you do measurement and feedback, and thermalize again. To measurement, feedback, thermalize again. That's the best protocol you can do. So that's what we were doing, and we were happy to see that the computer says the same thing. So it's yeah.
Is the time step, is that an input or is that something that's output?
It's the time, it's an input. So you just define your time step. What is your time step? So it's at each step you define what the computer gets the state, right? So for, let's say, Si and Si plus 1. So Si is the state at time t, and Si plus 1 is t plus dt. So it's a time series analysis in that way. So yes, so that would be all. Thank you.
Did you drive any kind of fluctuation theorem for your system as well? Because you have forward probabilities, backward probabilities.
Yeah, I think there's a nice article from Srinath and Sriyal from our group. They worked on this closed system theorem and then error of time, but I haven't worked on that.
So in the second case, I mean, you looked at like 3 qubits and combining the measurement result of these 2 qubits.
Yes.
Do you think it would be even better if you have 3 qubits and you combine the measurement result of the 3 qubits?
I think it's a collective effect. So I think if you increase the number of qubits, it should get better, I think. That I don't see any other way of explaining this behavior apart from like that.
In your measurement assisted refrigerators, it's schematic. I'm not sure what exactly the couplings are, but this reminds me of a shielding hex group where they have, 2 qubits coupled to a hot bath and a cold bath. That diagram is fine.
Yes.
And there is a point where you get a heat current through the system that leads to the 2 qubits being entangled, and the heat current exceeds a certain threshold and there's entanglement between 2 qubits. And I wonder if there's a connection between those two, and you're making these local measurements and breaking that entanglement that's generated between the two.
Yeah, I think the reason we get this heat extraction just due to the measurement, I think has something to do with the entanglement, but we didn't explore further on that topic. But the coupling is, in this case, we have like sigma x coupling between the 2 qubits. So qubit is in the sigma g basis and sigma x coupling between 2 qubits, so that we have like a global basis which we can look. So we just diagonalize the Hamiltonian, and then we study the master equation in that diagonalized basis, but we do the measurement in the local basis.
And then the coupling to the baths is just like a gamma plus.
Exactly, it's just like tunneling. Yes.
But here, so it's really like just measurement, and then you do like unitary evolution, but that do not depend on the measurement result.
Yes, that doesn't depend. That's why we don't call it a feedback. We just call it a rotation.
It's crazy.
Yeah. It's just so we just thought, why let's flop them and see what happens, and then we get better results sometimes, and so that's some additional results we can put.
So do you have like analytic expressions for characteristic function as well?
No, we didn't do like so by characteristic function you mean different from where you can get different moments of.
Yes.
No, we didn't do that. We just wanted to calculate like density matrix and the currents.
Because you were showing like probability distribution, analytical expression for probability distribution, something like that.
This one?
No. During I think your second part of the problem. Before.
This one? This one was just from numerical simulation. There is no master equation involved, so.
Okay.
It's just like you do measurement, you have the density matrix and look for like the energy. So it's like a step process, right? So you have like the qubit is like, it's not always in contact of the thermal bath. So at one point, so you just thermalize at the end. So you save all those calculations.
Okay.
Any more questions for Bibek? Thank you, Bibek.